All right. Good morning, good morning, good morning. Or afternoon. Or exactly noon. So it's not really morning, is it? I mean, it's not really morning or afternoon if it's exactly 12 o'clock, is it? I mean, afternoon. Hold on a second. Just give me a minute here. I mean, literally a minute. It would be weird to have a minute of dead air, so maybe I'll just keep rambling. Good day, kind internet. Welcome to day two. Oh, hold on a minute. Hold on. Stream information says day one. Got to update Reno. Day two. Wow. Day at. That's not right. That's a capital two. There we go. Update information. Haha. There we go. Now, 12:01 p.m. Good afternoon. Good afternoon, internet. Welcome to the Twitch stream. So today, I'm going to be covering a few different topics. I think if you're one of my students from my Academy Canada class, you've gotten an email sent out just now explaining which topics I'm going to cover. If not, hopefully you're along for the ride and can just buckle up. Buckle up. It's like the comedians say, right? Whenever someone tells you to buckle up, like this is going to get intense, you better buckle up. It's going to be the most tame, pedestrian, like annoying nonsense ever. So you better buckle up for this math work, boys. Let me tell you, it's gonna get rough. Boys and girls, of course. Right? But on the internet, everyone else on the internet is the same like overweight guy in a basement with like 100 different monitors. Not that I'm not that I've got 100 monitors. I've got three. I've got three monitors. So that's less than 100. Fewer than 100. Boy, I almost said less than 100. I almost said less than 100. Can you believe that? Can you believe the math/English teacher almost just made an error with less or fewer? Boy, oh boy, that's a cross-curricular lesson in both subjects that I teach. Oh my God, what am I doing? I'll tell you what I'm doing. I am about to start doing, let's see, Math 3101B, page 18 to 19. That's what's up Math here. Math 3101B, page 18 to 19. That's what's up here. Math 3101B, page 18 to 19. Okay, so I'm going to zoom in on that a bit so we can maybe see it a bit better. Okay, so I'm going to zoom in on that a bit so we can maybe see it a bit better. Okay, so I'm going to zoom in on that a bit so we can maybe see it. What is going on my desktop? Oh, whoops! You'd think I'd never streamed before. I just brought up my stream and left the sound up. I was like, why the heck? Why the heck am I looping? What is even going on here? Boy, oh boy. Boy, oh boy. The things that I do. The thing. Great. It's good stuff. It's good. I'm already. I'm what? What am I? 3 minutes and 20 seconds in. Boy, we're already going next level here, aren't we? So, I don't know if that actually came through on the stream. Hopefully it didn't. I did try to set up OBS so it wouldn't be capturing my desktop audio. I'll see afterwards if maybe I'm just rambling for nonsense reasons. But in my headphones, I was hearing myself looping, which was quite odd. Anyway, let me just turn my camera a touch. Here we go. I want to get the same perspective. So, I'm going to start in with Math 3101B, pages 18 to 19. Now, these pages are good to start off with because they're a good jumping off point from what we were talking about yesterday, right? Because yesterday we were talking about graphing. We're talking about graphing on graphing calculators specifically, like this old TI-84 here that I got. See that? See that guy? Yeah. We're going to use that then to graph some of these lines here. See these ones? These ones up here in the corner? See if you can, oh, you can't, oh, okay. For whatever reason, you couldn't see my cursor there for a second. There it is. Okay. Lots of things going on at once. I'm going to try to stop scratching my nose so often. I noticed it. I was watching my video from yesterday, and I was doing it constantly. But these allergies, I promise it's allergies. You're not going to catch anything from me, at least not over the internet. But it's most definitely allergies. Anyway, so we have some parabolas. Parabolas are great. See this guy over here? Right? I'll zoom in a little bit so you can see that one better. But that is a parabola, so that is a curved line, right? And that is described with a quadratic. Now, a quadratic is an equation where the highest exponent on a variable is 2. Right? So here, you see for A, the highest exponent on a variable is 2 because of this one. Right? The exponents are the numbers in the corner. The variable are these x's. Right? So the highest exponent on a variable is this 2 up here. Now, this example wants us to sketch each polynomial function, determine the following characteristics for each function. Possible number of x-intercepts. Well, we can determine the exact number of x-intercepts too, but we'll also determine the possible number. That's easy. The y-intercepts, the end behavior, we want the number of turning points, the domain, and the range. All right. Oh, we are actually going to get on to a cubic as well, not just a quadratic. Okay. But first up, for A here, we have a quadratic. So this is a really good one actually to talk about because it's reviewing a few things from previous courses. So even if you're not currently doing Math 3101B, if you're doing any of the if you're doing the academic math program, you will encounter this kind of stuff eventually, and you're probably already seeing some stuff that's similar to this. All right, so I'm going to go ahead and show you basically how we can graph this guy. But to find the vertex, like it says here, right? The vertex is x equals negative b over 2a. So the vertex of a quadratic is described by x equals negative b over 2a. Now what does that mean? Well, in any quadratic, we know that the basic form is y equals ax squared plus bx. Oh, I'm getting ahead of myself. Plus bx plus c. Right? So this is the a goes here. It's the coefficient on the first term. The b goes here. It's the coefficient on the second term. Right? So let me just zoom out a little bit over here in the corner. Right? Now, remember, this is getting us only the x coordinate of the vertex, right? Which is why c here doesn't matter, right? Because we know that c is the constant. It's what slides the parabola up or down, right? And no matter how far up or how far down it is, the x coordinate, which is the horizontal coordinate, is going to stay the same. Because of course, right, our coordinate plane as x is here and y is here. So if we have our parabola, say, here, or if we slide it up to here, or slide it down, say, to here, imagine that was the same one, right? The vertex of all these ones are still going to be in line, provided I drew them correctly, right? Which is why the c term doesn't actually matter when we're finding the x coordinate of the vertex. But you should already be familiar with thinking of this as A, B, and C, right? Because that is what we use to solve everyone's favorite math equation, which is, of course, we all know the quadratic formula, obviously, right? Negative b plus or minus the square root of b squared minus 4ac all over 2a. All over 2a. There's an old YouTuber, some sort of video, just like someone singing a song they made up about that. I think that was like pre-YouTube years, like back in like the time when people watched like prehistoric websites like Joe Cartoon and CampChaos.com. Yeah, I'm like an internet dad, right? I know my Napster bad memes. Yeah, that's right. The greatest story ever told. Or the ultimate battle of ultimate destiny. Boy, let's trip down memery lane here. Anyway, so when we're trying to find the x coordinate of the vertex, we're just going to plug these in the same way we would plug them in if we were using the quadratic equation. With the quadratic equation, solves for the roots, right? This finds the roots, whereas this, negative b over 2a, finds the x coordinate of the vertex. Very useful things to know, right? So here then, we have y equals negative x squared plus 7x minus 8. Right? So, one useful thing to do whenever we're approaching any question like this is to declare our variables first. So just over here on the side, we're going to write down what we know, basically, right? We know that C is a negative 8. We always take the sign that's in front. That goes along with it. That's important. Right? Let me maybe zoom my cam in a touch. Okay. B is the middle one, so B is going to be a positive 7. And now A, what do we put in for A? It's just a negative sign. Well, that means it's a negative 1, of course. Right? So that's why here we know that our x-coordinate of our vertex is going to be negative 7 over 2 times negative 1. So x is 7 over 2, or here they were real Philistines, and they went ahead and turned that into a decimal. X equals 3.5. It's fine. It's, it's a rounded decimal. It stops there. It doesn't carry on going, right? So that's it's a reasonable one to round to a decimal, I think. And then to find the y coordinate, we just go back and we substitute this guy into the original quadratic, right, in place of x. So we have y is equal to negative 3.5 squared plus 7 times 3.5 minus 8, right? And then on here they go ahead and they do it out. I'm not going to grab my calculator. I'm just going to write it down from there, right? Plus 24.5 minus 8, which gives us a y coordinate of 4.25. Okay. So what I'm going to do now, what I'm going to do that's different than what the book shows here, is I'm going to show you how we can take this info and then sort of graph it to find out what's going on here. Now you can use a TI-84, like my good pal over here. I like that one quite a lot. But if you haven't got that, you can also use a Desmos calculator, which I will show you right now. Let's hold on a sec. Watch this new technology. Check this out. Whee, whee. There we go. Look at that. Yeah, there we go. Good stuff. So this is a Desmos window here. This is www.desmos.com, DESMOS/calculator. Right? And, oh, let me close down my downloads menu there. I was skewing things up. So over here now, I can just plug in this equation that we had from before, from the document, right? Which was negative x. You can see it changes as it goes through, right? That's pretty cool. Negative x squared. Oh, there's negative x squared now. Negative x squared plus 7x minus 8. There it is. There's your graph. Marvelous, right? Look at that. So, yeah, Desmos will automatically put it in as y equals, the same as like a TI-84 calculator would do, right? Yeah, and you can see from here now, we know that what we found was that the x-coordinate of our vertex should be 3.5. Well, let's go and see. They give us the point here. Hey, look at that. Look at that. They even give us the vertex for us. It's right there. It is 3.5, 4.25. Hey, and that turns out to be exactly what we found back over here, right? 3.5, 4.25, right there. Easy stuff. Right? Good. So now let's go back to our document over here, and let's answer these other questions. So, graph opens downward, max graph, check. Number of x-intercepts, that's going to be 2. Right? So if I switch back over to my Desmos, we see x-intercepts are 2, because there's one right here, See, it even gives us the values for those too when we mouse over them. Pretty useful program. And then this is the other one over here. This is what we call the roots. So those two numbers would have been what we would have found if we went ahead and did this. If we went ahead and did the quadratic equation here, we would have found the roots of this quadratic. So if we took these variables, plug them into this formula, what we would have gotten would have been 1.438, and we would have gotten 5.562, right? So those are the roots. But now we've been asked to find the number of x-intercepts. That's going to be 2. We've also been asked to find the y-intercept. Now we can't see the y-intercept on this Desmos, but I can just grab it. Look at that. Look at that. I can just grab it and move it around. I can slide it and woo. Okay. So we look down here. I can zoom in too with my mouse wheel. Look at that. Dun, 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 dun. Gonna need a bigger graph. It's a Jaws reference. Okay. Y-intercept, -8. That's right. -8's right here. Oh, I kind of wanted the scale to get a bit bigger so you guys can see it on stream a little better, but as I keep zooming in, the scale remains the same size. It's how elusive. Anyway, yes, -8 is indeed the y-intercept. End behavior, well, all the end behavior is to tell us what quadrants it extends into. And of course, this is a parabola, so it's never going to end. I can just keep on scrolling down and down and down and down and down and down and down. And it's never going to get to a point where it ends, because they always carry on infinitely. But what you're asked to say is what quadrants it ends in, right? So, well, not that it ends in, what quadrants it continues into, to be very precise. So, what we have there, quadrants it continues into, as we see over here, are going to be Q3 and Q4. Q3 being the bottom left, Q4 being the bottom right. Because the numbering starts in the top right, then goes counterclockwise, or anti-clockwise, depending on where you are, who you are, and where you're from. Number of turning points, 1. Right, of course there's one turning point. All quadratics are going to have one turning point. Right, we see the turning point. The turning point is right here. That's what this guy is, right there. That's the turning point. See? Okay, all quadratics will have one turning point. Cubics will have 2, and straight lines will have 0 because they're a straight line. It's right there in the name. And the domain, right? We had to find the domain and the range. Now the domain and the range for a quadratic like this has a bit more work than the domain and range for a straight line. Obviously, the domain and range for a straight line is just all real numbers both times. Right? For here, the domain is all real numbers, so we can call that x is all real numbers. I might have to rig up a scene where it's got my writing and also Desmos. Yeah, I'll make a note of that actually. Desmos with doc cam. Right. You know, it's a work in progress. I mean, this is public access TV, right? Oh boy, there's me watching my stream. Look at this. Whoa. Okay. Okay, this is cool. I'm just gonna leave it here for a second. Dun 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 dun. Yeah, this is good. This is good. This is the content that people tune in for. All right. Yeah, I've nothing. You know, my ability to distract myself never fails. Let me tell you, just something shiny like on the internet or something like that. No, I'm all into that. None of this like doing work stuff is nonsense. All right, so the domain is all real numbers. That's the point of my story. The range, well, the range is the number of y values that it takes up, right? So it does have a max on the y, right? And that's the y coordinate of the vertex. One reason it's so useful and important to find the vertex is because the vertex tells us useful information about the range, right? Because if we go back over to the working display over here, right, we will see that the range is that y is less than or equal to 4.25, right? We see that over here. y is less than or equal to 4.25. Now, where do we find this 4.25 already? Well, of course, right here, right? That was the y coordinate of the vertex. So obviously that makes sense, right? Because if we go back and look at the old graph itself, the vertex is the highest point, right? Or if it was the other way around, the vertex, say if it was this, right? The vertex would be the lowest point, right? Of course, the graph changed totally when I switched that sign there, you know. One nice thing about Desmos is it's actually super kind about these things. Like unlike a TI-84, where like one type of X works and one type of X doesn't. In Desmos, you can just type X with your keyboard and it works, right? It's yeah. So again, this is a super useful program for y'all doing math work, especially math work from home. Okay, so that's it's a good look at that point. Let's do well the straight line. The straight line maybe I'll go over a little bit quicker. So let me show you yet another scene that I have. Whoa, kidoki. Um, there we go. Yeah, that's how it's supposed to look. Okay, maybe I could maybe make myself a little bigger here. Let's see. Oh, nope, that's moving me. There we go. Now I'm bigger. Yeah. And my dock cam, oh, that's a bit bigger too. There we go. Okay, maybe I could even slide this one over. Slide it over, sliding it, sliding it, sliding it. Okay, make this one a bit bigger. Yeah, make this a bit bigger up to match. Let's see, let's get this matched. I'm just gonna do my stream prep like on stream. It's totally cool. Yeah, don't worry about it. Okay. All right, we'll go with this. We'll go with this for now. Actually, I don't need to be so big, do I? No, I don't. My document cam needs to be bigger though, because that's tough to see there. Marvelous. We'll go with that. We'll go with that for right now. I'll center myself. Okay. Enough fiddling. Enough fiddling with the cams here. So we see here now, we've got the document sort of blown up a bit. The next question on this page that I was asked to cover is a straight line. Now I'm not going to go through and do that one out by hand as much because a straight line's a lot more straightforward. No, I mean, I guess pun intended. It's y equals negative 4x plus 1. Right? And now a line is, the generic form of a line is y equals mx plus b. If you watch this stream more than once, you'll probably see me go over this every single day. It's a really common topic to bring up, where m is the slope, right? And b is the y-intercept. Okay? So we can see that over here, that the y-intercept is a positive 1. The slope is a negative 4, right? So I'm going to go over this one a bit quicker, like I said, because this course doesn't deal with straight lines as much, and you should already have seen these. But the number of x-intercepts is, of course, 1. Any straight line is going to have 1 x-intercept, unless it's horizontal. Like, unless it's perfectly horizontal, it's always going to have an x-intercept, right? So that would just be a line like, y equals 2. That's never going to cross the x-axis. Y-intercept minus h in behavior Q2 to Q4, right? So it goes from Q2. Q2 is the quadrant over here. Goes down toward Q4. That's the quadrant down here. Domain is x is equal to all real numbers. Range is y is equal to all real numbers, right? Because it's a straight line. So next up, we have our cubic. Now this one is a bit more of an interesting one. So let me go back over so I can see this a bit more clearly on my paper here, right? So I'm going to recommend for a cubic that we just go ahead and graph them, actually. I think that is probably the easiest way to go about you guys solving these ones. Um, on a test, if you have to do a cubic, you will have access to a graphing calculator, right? Um, so I'm just going to get you to go ahead and we're going to plug this one into our old pal Desmos over here, right? So let me just flick back to that screen, clear off the previous one. You just click X up in the corner. And then what we have is y is equal to 2x cubed. The way we do cubed is the sort of shift 6. Well, shift 6 here. It's different if you're in the UK as we might call it. So just let me show you my fancy keyboard. It's right here. This one, shift 6. That's the symbol that we use to get the power of something, right? Go back over to Chrome. So 2x to the power of 3 plus 3x to the power of 2 minus 4x plus 5. There she be. That's it. So this is our cubic, right? You actually won't be expected to graph one of these, right? But you will be expected to, based on the formula, be able to know how to graph it, right? You won't be expected to like graph by hand. I mean, so then what do we have? Possible number of x-intercepts. Well, our possible number of x-intercepts doesn't require you to graph it to know that, right? Because if we go back over to here, we see it asks for the possible number of x-intercepts. Now, possible, without graphing it, we would always say 3, right? It could be 3, it could be 2, it could be 1, but I mean 3 is I guess, the maximum possible, right? But once we graph it ourselves, we, can know y-intercept is going to be positive 5. We know that the y-intercept is positive 5 from the equation, right? And where do we see 5 in the equation? Well, 5 is the constant. It's this number right here, right? So we know that this one has a y-intercept of 5. The end behavior is going to be Q3 to Q1 because that's kind of just how cubics will generally go, right? But you can see on our Desmos, if we switch back over here to Chrome, right? There it is. This is Q3 down here. This is where it's coming up from. And Q1 is this quadrant over here. That's where it's heading toward. Okay. And what else? Domain and range, all real numbers. Yeah, because it continues up and down and left and right infinitely. Okay. I was also asked by the same student to go over these terms here. So let us make that look odd and then switch back over to here. So we have degree. Degree is the highest exponent on the polynomial is the degree of the polynomial, right? Like you've been hearing me call things quadratics and cubics. Those are just fancy names that we use for second degree polynomials and third degree polynomials, right? So the exponent in the corner tells us the degree of it. So say, for example, we had like x to the 7 plus x to the 2 minus 14. I don't know, right? This is now a 7th degree polynomial, right? Because we don't call it like, I don't know, septuadratics or something. We don't need to remember some, Latin nomenclature in order to determine what polynomial we have. We just call it a 7th degree polynomial, right? Which is one reason why it's a little bit funny, where on like high school tests and stuff, they'll always ask for things like, oh, what do you call an 8-sided figure? An 8-sided polynomial. It's an octagon. Yeah, but like mathematicians are just maybe you call it an 8-gon, right? 8-gon, 9-gon, 10-gon, right? Who cares? Who cares if it's what nonagon? So I don't give a shit. Oh, don't give a poop. It's a G-rated stream, right? It's right down there. It's a G-rated stream. Okay, So leading coefficient, the coefficient of the term with the greatest degree in a polynomial function in standard form. All right, so back over to my arbitrary example here. Say there was a 3 here and a 6 here. The leading coefficient is 3 because it's the coefficient, the number multiplied by the variable with the highest exponent. I mean, before it would have been a leading coefficient of 1, but then this one also has 1, so it's not, it's not a stellar example. And the constant term is a polynomial in standard form, is a term that does not have a variable. So here, our constant term is negative 14. Right? When a polynomial is in standard form, the maximum number of x-intercepts the graph may have is equal to the degree of the function. That's right, because it's equal to the number of times it turns. Right? A straight line has degree 1. It's like this. It can only cross the x-axis once, because once it goes, it's never turning back. A second degree polynomial is like that. It can cross the x-axis twice because it turns once. I think you're seeing where I'm going with this. A third degree polynomial turns twice, so it can cross the x-axis 1, 2, 3 times potentially. Right? Not hard to guess that a seventh degree polynomial is going to turn how many times? Okay, nobody told me. 6. 6 is the answer. All right, and what else do we have here? The degree and leading coefficient of the equation of a polynomial function indicate the end behavior of the graph of the function. Right, yes. So the leading coefficient of the equation, if it's negative, it'll switch, right? So for example, this quadratic that I've drawn here, this is a negative quadratic because it's facing downwards. A positive quadratic would look like that. But it's the first term that determines the end behavior. Now that's going to be a bit different for each different polynomial. That's one you can either remember it or you can graph it. You can graph them with Desmos, you can graph them with the calculator, and you'll learn it after a while to remember which one is which. Okay. The constant term in the equation of a polynomial is the y-intercept of the graph. That's right. The constant term slides it up, slides it down. Right? Because in standard form, right, y equals mx plus b here, the b is the y-intercept, like it says. And y equals mx plus b is not like all that different. This is just sort of the logical extension of y equals mx plus b, because this is just the generic form of a first degree polynomial, which is otherwise known as a line. Right? So the more you learn about math, the more you'll see that it's all really kind of connected, you know. It's that's honestly, it's probably the most interesting thing about it, is that as you get more into it, you start seeing, hey, these things they're all actually kind of the same thing, but just more complicated versions of it with different types of arithmetic mashed into it. It's a very elegant way of summarizing an entire, you know, discipline of art/science. Anyway, that is Math 3101B, pages 18 to 19. All right, so Tia, that was your submission. Thank you very much for that. I hope my 30 minutes of rambling has answered a question or two that you might have had. Now, what am I going to go next? Let's see here. We have got let's take a little bit of a turn here. Let's go to something. Let's go from a grade 12 academic to a refresher. What I'm going to do now, this one is just a little bit more for Renetta here. Now, Renetta, if you're not watching this live right now, I am going to send you a link to the stream afterwards so you can see this. So, hello, future Renetta. This is past Peter. I mean, past shit. She read the stream. Past NL Mathman. That's right. That's right. I don't have a real name. Okay? Don't try to dox me. Don't at me. I mean, you can at me if you want to. You know, that'd be kind of cool. So, this was Renetta's stuff from yesterday. Let me fold that one down and carry on. So I'm going to do page 169. Nice. So, again, just to sort of reiterate from yesterday, I haven't gotten a more higher resolution document cam yet because, you know, I mean, that should be enough explanation, right? I mean, this is, March 24th, 2020, and I'm living in Canada, so you maybe can figure that out the rest of it. So this one here is a dot on both ends. Because there's a dot on both ends, we know that, the line ends, which means it's not a line because lines go on infinitely. This one is a line segment, and it's line segment ME or EM, depending on which order you want to write it in, but since it goes from M to E, left to right, I'd say 99% of people are going to write it as ME. And now I'll get work in with it written as EM just to prove me wrong. This next one, we see that it's got an arrow on one side and a dot on the other, right? So this one is a ray. It's ray RD. It could be RD or DR, but the important part is that the arrow has to be, oh, my mistake. Oh, look at that. Yes, almost. Good thing I caught myself. The arrow is not that way, the arrow is that way. Right, so it can be RD or DR, just the arrow needs to be on the proper side. Right, and this one over here, 1C, this is angle. That's the symbol we use for angle. And remember, this is angle PTA or angle ATP. So it's either a parent-teacher association or it's adenosine triphosphate. That's right? Adenosine triphosphate. That's some phrase that I remember from biology. I'm not sure what it means. Something to do with muscles, maybe? Energy, metabolism? I don't know. What is science? I don't understand. Even though I do occasionally teach a science course, but never you mind. Next question. Compare the angles of each triangle, the model of a right angle, then tell whether the triangle is acute, obtuse, or a right triangle. The model of a right angle, what the heck does that mean? Well, how can we do that? Well, we can get our handy dandy math set. Math set that I took from classroom, and of course I wiped down diligently with my Clorox wipes. So I can use this. This is a right angle, or the one in here, either one, right? So, hey, it lines up. Look at that. It totally fits. So this one is definitely a right triangle. Now that's a way to use it like as a stencil, right? If you ever see a thing called a carpenter's square, right? When I was a kid, like my dad does lots of carpentry and various, like every handyman thing known to man. He had this like triangle looking thing, and he was like, "Pass me that square," and I was like, I might only be 7, but I sure as shit know a triangle when I see one. Sure as poop. Look, it's hard, all right? It's hard when you're at home sitting in front of your computer and you're used to like, cursing your mouth off when you get a resist in a Warsaw Gulch game or something. It's hard. It's hard. It's a change of pace, is what I'm saying. We're all getting through this together. All right, So 2A, it is indeed a right triangle because it has a 90-degree angle. 90-degree angle right there. We can see that that is indeed 90 degrees. This one is an obtuse triangle because if we were to take this and measure it like so, now I'll show you. There we go. So I'm measuring it by lining up the bottom side with the bottom side of the triangle with this black line in the bottom of my protractor. The sort of crosshair, or this part here in the middle of the protractor, is lined up with the vertex, and then I count from the 0 that lines up with this side of the triangle. See? So I measured the bottom side of the triangle, so I start with this 0 because it's the inside 0. Now I go, it's 120 degrees. Not super important for me to have known that was 120 degrees for this question, but you will be asked to measure angles at some points. That one, because 120 is an obtuse angle, an angle that's greater than 90 degrees but less than 180, this is an obtuse triangle. Right? And this one over here, all these angles are smaller than 90. We can even see that at a glance. So that means this is an acute triangle. All right, this is page 169. Oh, crap. I'm marking up my my teacher's copy. What else have we got then? Down here. Yes, this is a good one. This is the real, like I said yesterday, this is the noodle boiler. This one here. Which figure is a square? Well, which figure is a square? You can see that it's A, right? If you got to, you can break out some sort of measuring tool, right? My math set doesn't have any rulers, but I do have these. Well, it doesn't have any straight rulers. It has these triangle rulers. So I can just measure that. See that this side here, 2.5 centimeters. This side here, 2.5 centimeters, right? And we can measure, if we really wanted to be extremely precise, we would measure these and say, is this 90? Indeed it is, right? These angles are 90. Those two sides are equal. They're all going to be equal. So figure's a square, A. And the other one's a square. Well, this one doesn't have 90-degree angles, obviously not a square. This one doesn't either. And this one, obviously, the sides are different lengths, so only A. Which figures are rectangles? Now, a very, very, very common mistake that I get on these sort of tests and assignments is when someone asks which figures are rectangles, they say just C, and they get half marks, or maybe no marks. Depends on if they got my coffee order right that morning, right? So here, A and C are rectangles. Which figures are parallelograms? Well, parallelograms are figures that have two pairs of parallel sides. So here, you may be tempted to say B and D are parallelograms, and students frequently do, because they're used to hearing of parallelograms as shapes that have slanted sides, like not 90-degree angles. But the thing is, a square is a parallelogram. A rectangle is a parallelogram. Right? So actually, the correct answer here, excuse me, is that all four of these are parallelograms. Which figures are rhombuses? I don't like rhombuses. Rhombies. Which figures are rhombuses? A and B. Now remember from yesterday, a rhombus is when all the sides are the same length, but they needn't have 90-degree angles. So if we were to measure the sides of B here, we would see that is 2.5 centimeters. That is 2.5 centimeters. That is 2.5 centimeters, etc. Right? So but we know that A is also a rhombus, even though generally if you gave that to somebody and said, what shape is that? They're not going to be like, a rhombus. But it is. It is a rhombus. It is also a square. Okay, so that was covering that other page. So Renetta, hopefully that was somewhat helpful for you. And that was, let's see, Prism Math Blue, page 169. Good, good. Okay, let's close that one up. Next up, yeah, I'll move ahead a little bit here. We're going to do Math 1102A, Unit 2 Review Sheet. Math 1102A, Unit 2 Review Sheet. Now, just to remind you, if anyone is watching, you can indeed submit questions to me if you want me to solve any. Just let me know. Let me know as best you can in Twitch chat, or if you're one of the class students, you can email or Skype or whatever. But you can also use Twitch chat. I would kind of recommend that. It's a free account, of course. And then if you have anything else that you're working on, I will get to that after I get to the ones that I've announced that I'm going to be doing. Okay. So here we're going to start with 1102A Unit 2 Review Sheet. Now this one is, I believe, Ashley submitted this one. So let me, my God. We go over here now. So this is me moving my camera. So 1102A review sheet unit 2. Okay. So as we see up here in the corner, that is mostly about measurements, right? I'm not going to go over all of these ones. Like, what imperial unit was a contractor used for dimensions of a bedroom in a typical home in Mount Pearl? The feet, obviously. The only, the only, I guess, substantial part of that is to know the difference between imperial and metric. Imperial is, the old system. Lots of countries have different names for it these days, but imperial is the one where you're never sure how many of one thing go into how many of another, right? Whereas metric is where it's always tens. What referent could you use for 1 yard? 1 meter, 1 millimeter. I don't know. 1 meter, the width of your desk. 1 millimeter, the width of a coin. 1 yard, the width of your yard. Obviously, like your yard should be about a yard, right? It just stands to reason. I mean, don't actually do that. No, a yard's pretty close to a meter. Actually, a yard's a little bit shy of a meter. So whatever referent you give for meter, you could give the same one for yard. Referent just means like a common real world object that would be about that long. Convert each of the following. Okay, let's do a few conversions. So these are relatively straightforward. I'm going to zoom in a whole bunch here. But we are converting to some odd metric measurements that don't come up a whole lot, right? We're converting millimeters to DM. What the heck is DM? Direct messages? Why am I converting? I'm not converting megamen to direct messages. This doesn't make any sense. What's going on? Well, along with this, you will also have this thing over here called the SI unit conversion ladder. SI is just a fancy way to say metric, or a less fancy way to say metric. I don't know. Système International. Oui. So over here, this is our. Let me zoom in a touch. Okay, sorry, I just had a little bit of a distraction. All right. Just a second here, please. Sorry, I'm going to try not to send emails and do too much other contacting while I'm on stream. But yeah, I have some students doing tests this morning, so that sort of does take priority. Okay, so to go back to explaining, yes, this over here, this is what we call a SI unit conversion ladder or conversion steps or whatever phrase you want to use. But this shows us basically how we convert from one metric unit to the other, including all the obscure ones, like these ones over here, right? Like kilometers, obviously that's a common one, but hectometers, decameters, decimeters, how often do you hear about that? It is interesting though. It is one thing that's interesting is in well, there's more than one thing that's interesting, but in the UK or the EU, which are apparently different. Don't want to get political. Uh, you'll see sometimes centiliters on like drinks, alcoholic beverage and stuff. Like you'll see like 70 like centiliters. What? What is a centiliter? Well, a centiliter is 10 milliliters, right? In Canada here or in the US, you'll just always see it. Well, actually, I don't know about the US. The US is bonkers. But in Canada, you'll always see it in milliliters, right? Like, so there'll be a 700 milliliter bottle. But if you were in Europe, you might see that as 70 centiliter bottle. I never saw a deciliter. I never saw deci anything like used anywhere. But yeah, centiliter being used was that was an odd one to me as a Canadian. Although our measuring system is foolish. It is almost as foolish as the UK, where they ostensibly use the metric system, but then they like speeds are measured in miles per hour, and like weight is measured in stone. I don't even know what that's supposed to be. Stone? I don't know. I don't understand. Anyway, so if we're going from meters, you see in the middle here, they're using meters as this one, but the second letter, right, well, or the third letter in the case of deca, um, isn't really all that important. What's important is the prefix, right? So whether it's meters or liters or grams or I don't know, anything else, flops, teraflops, petaflops. No, those are a bit different. Computer things are a bit different because of the way binary works. Um, but yeah, whether it's meters or liters or grams or anything, um, it's the prefix on the front that determines how we convert one to the other, right? So if we're going from meters to decameters or decimeters, which one's which? Decimeters, we're going down one step. If we're going down one step, we're going to multiply by 10. Like it says here, multiply by 10 for each step. Now it's another 10 that we multiply by, right? So if we're going from meters to centimeters, we already know that 1 meter equals 100 centimeters. We already do know that, right? And the way I like to tell people to remember that is that cent literally means 100. Cent en français is 100. Of course, there's 100 cents in a dollar, there's 100 cents in a euro. You know, it's an easy one to remember. Pence is maybe a bit different. It doesn't quite sound like cent. You could call it, you know, but it is still 100p in a pound now anyway. Um, Not, you know, 10 years before I was alive or anything. Back then it was different. I don't remember that very well though. So, and if we're going up, we're going to divide. If we're going down, we're going to multiply. But we're multiplying not by an additional 10. We're multiplying by 10 again, right? So if we're going down, say we go down 3 steps, say if we're going, you know, meters past dm, past cm, and all the way to mm, all the way to millimeters. This is going to be a 10 times 10 for this one. It's going to be a times 10 for this one. And it's going to be a times 10 for this one. So we're going to have 3 multiplied by 10s, which is not 10 times 3. It's 10 to the power of 3, which is 1,000. Right? Or a 1 with, hey, look at that, 3 zeros. Pretty good, right? Straightforward. So if we're converting from meters to millimeters, which you should probably already know, you're going to times by 1,000. Right? Same if we're going up. If we're going up 3 steps, say we're starting at, I'll write it the opposite direction. Starting at meters, right? Again, we're going up to decameters, up then to hectometers, which are obscure and bonkers, then up then to kilometers, kilometers, which, I mean, you hear those all the time, right? At least here. So now it's going to be a divide by 10, a divide by 10, and a divide by 10, right? And again, or that one over there was multiplied by 10 to the 3, which is multiplied by 1,000. So here it's going to be dividing by 10 to the 3, right? Which is the same as dividing by 1,000. And of course we know that if we want to get from meters to kilometers, we divide by 1,000, right? If something is 2,700 meters, that of course equals 2.7 kilometers, right? This is probably old hat. You guys know this stuff, but I just wanted to go over how exactly we read this sort of graph here. Because when we're doing one like this, right, and we've got these obscure sort of ones that we've never seen before, well, that's when you got to break out your metric steps, right? I remember one of the very first activities I ever made as a teacher. I was teaching at a school in Harlow in Essex in UK, and they asked me to make up a activity on metric system, right? Now, me having just come from Canada, like I had never made any other activity in school, like ever. I was just a student teacher, and this was like the first thing I did in my internship, pretty much. Um, I went ham. I went ham on that one. I included decameters, hectometers. I didn't go crazy into like micrometers or anything like that, but I used a lot of the ones that are showing on here, right? And I mean, in my defense, it was to like a grade, was it grade 10? No, grade 9, year 10. Yeah, it was a year 10 class. And they were middle to top set. I don't know. They should have been able to know this stuff, but the teacher looked at the teacher didn't look at my activity before I gave it to them. And then when I gave it to them, she was like, "What in the world is this? Like I haven't even seen these before. What what metric prefixes are these?" And I was like, "Sorry, when I was quizzed on these in Canada, the teachers broke out all the obscure ones because they were always trying to trip us up a bit, right? I didn't realize that kids would just have had no contact ever with the obscure um, bits of the metric system. Anyway, so for question 4A, we've got 127 millimeters is equal to some number decimeters. So we pop back over to our other sheet, or we can just see it on here in this one that I've already written out. We see that millimeters, to get to decimeters, we've got to go up 2 steps. 1 step, 2 steps. If we're going up 2 steps, we're multiplying by 100. Oh, sorry, we're going up 2, rather. No, we're dividing. If we're going up. Down is multiply. Up is divide. So we're going up 2 steps. We're going to divide 127. It's going to be divided by 100. Generally, we don't write out the division sign like that. We'll just do 127 over 100. 127 over 100 is, of course, 1.27. So 127 millimeters is 1.27 decimeters. Right? And then for B here, if we were to do centimeters to hectometers, we have 976 cm. Well, to get from cm to hm, what have we got to do? Well, that one's not on my sheet here, so I'm going to pop back over to my document here. So from cm, we're going to go one step up, 2 steps up, 3 steps up, 4 steps up. So we have to divide by 10 4 times, which is the same as dividing by 10,000. Okay? So we're going to do 976 divide by 10, 10, 10, 10, right? Just to show you 4 tens, we're dividing by 4 tens, not 4 times 10, 4 tens. So that's going to be 976 over that. So what this means is we just move our decimal left a number of places equal to the number of zeros, which is 4 places. So we've got our 976, and we're going to start here. 1, 2, 3, 4. The new decimal goes here. Zeros and zeros. So 976 centimeters equals 0.0976 hectometers. Right? You will not be expected to memorize those, but you will be given this sort of sheet on a test and be expected to be able to solve those. Okay, what else do we have in this question? Kilometers to meters, going to skip that one. Miles to yards, that one is, yeah, I'm going to skip that one because that one's multiplying by, was it 1760? I looked that one up yesterday. Multiplying by 1760. Meters to yards. Yeah, meters to yards and centimeters to inches. We have to go with our conversion sheet. I'll skip meters to yards because I believe I did that one yesterday as well. But I'm just going to quickly do the centimeters to inches one as an example, and I'll leave the other ones for the students to do when you get around to doing the sheet for practice. So this one now is a little bit different, right? Because E and F are a bit different because you had to use your conversion factor, right? And I'm going to show you sort of the same way to do it that we went over yesterday, where for that one we know that there is 1 inch for every 2.54 centimeters. That's sort of the usual shorthand that's used, right? And here we have a number of centimeters. We have 63 cm. And just to show you how to do it with the units canceling method, like we did yesterday, 63 centimeters multiplied by our conversion factor, which is 1 inch per every 2.54 centimeters. What that's going to get us then in our centimeters, you're going to cancel with centimeters, and we're going to be left with a number of inches, which is what we're looking for. right? They're looking for inches. So it's going to be 63 divided by 2.54, which gives us 24.8 inches. There we go. See? Just like that one. The other way to do these is with cross multiplying, which is also a very useful method, right? But cross multiplying, we could use the same thing. 1 inch per every 2.54 centimeters equals, well, now we have some unknown number of inches hanging out over our 63 centimeters. So we could cross multiply. Right? So just give me a second there. Okay, so when we cross multiply these, we're going to end up, again, like yesterday, I'm going to not write the units in after I start cross multiplying. But we're going to have 63 times 1 on the left, so 63, I'll do 1 times 63 equals x times 2.54. Now it's useful to write this one out just because this is an example of a cross multiplying difficulty that people have very frequently, which is what in the world do you do when after you've cross multiplied there's something left here by the x? What you have to do then is divide by that number. So you're going to have 63 divide by 2.54 equals x. And that was exactly the same thing we did over here. We're going to find that that equals 24.8 is equal to x. Okay? If I kept the inches, if I kept the units there, you would see that in this step the units would cancel. And we would be left with inches. Right, because the variable wouldn't have. Anyway, that is right. So that's question 4 there. It's a pretty thorough answer to that one. Zoom out. The radius of a circle is 4.6 centimeters. What is the circumference of the circle? That's a good question. That is a good question because that is the one that's covered in loads of courses. Anyone who's currently working on, say, Math 2020, the level 2 math, you're going to be doing this stuff. And anybody doing sort of any other math, you're going to see those carry on later on. So just to quickly go over this one. So this is again Math 1102A review sheet. Unit 2. Right? Okay. So the radius of the circle is 4.6 centimeters. What is the circumference? Well, this is fairly straightforward. We know that the circumference of the circle, now you'll be given this on your test, is equal to pi times the diameter. That's how it'll be written out. Right? We also know that the diameter of a circle is equal to twice the radius. Right? That's all there is. That's all there is to these ones pretty much. So if we know that the radius is equal to 4.6, the diameter is going to equal 2 times 4.6, or the diameter is going to equal 9.2 centimeters. Right? Easy. So then the circumference is going to equal pi times 9.2. And I know your textbook says use 3.14 for pi, but I'm not about that. I'm not about this 3.14 life. I'm about putting in pi on my calculator and getting it to 10 digits at least. Or, you know, guessing that the pi song. Was it the YTMND? There's the pi YTMND. That's good. Maybe I should play that as my stream background. Or was it Hard and Firm? I think it was Hard and Firm, right? Chris Hardwick and Mike Furman did the pi song. Am I right about that, or am I just? Oh hi, Lonely Girl. Have you ever taught math in different languages? No, I have not. I have not. I have only taught math in English, though in a few different countries. My French is not nearly good enough to teach math, though I can say an occasional sentence like "Où est la salle de bain?" My French is basically like from a grade 9 Canadian student. I can ask how to open the window and where's the washroom. Right, so 3.141592654 times 9.2, easy. Circumference is equal to 28.9. 28.9 centimeters. There we go. Question 4, no problems. So determine the perimeter of the given figure, inches and feet in inches. I'm going to skip Reno that one. Find the length and girth of the given figure. Tell you what. In terms of the measurement of the line, length and girth. Girth is just a fancy way of saying like the area of the end of it, right? I'm not going to go through everything here because I have assigned this one for a student to do, and they're not, well, not assigned, it's to do for like bonus points, and they're not through it yet. So, I think maybe what I will do is, for question 7, I'm going to take this one a little bit differently because plenty of courses that I teach here deal with cylinders. So I'm just going to take this one and use this as a teachable moment to cover the volume and surface area of a cylinder. Now, this is not exactly the stuff that is covered in this math course, but it's Japan have a very different but efficient math system for elementary equations. Your teaching is very interesting and new to me. Well, thank you. Thanks. I'm glad you're finding it interesting. That's really interesting though to hear of different ways that math is taught in different countries. That's really cool because of course, no matter what language you're teaching it in, the symbols and the equations and stuff, the math, the basics of it is all still the same, and it can be written in lots of different ways. But everything you're doing really works out in the end, right? It's one of the beautiful things about math, for sure. Okay, so I'm going to do first. I'm going to do the volume of a cylinder. Now that is not necessarily this question on this assignment, so I'm just going to scratch that one out, right? But the volume of a cylinder is simply the volume of any regular shape is the area of the end of the shape, which is this here, multiplied by the height of the shape. And we know that, well, the area of a circle is equal to pi times the radius squared. Complex 3D shapes to emulate multiplication. Wow, that is interesting. I'm gonna have to look up what that means. That is, yeah, okay. Let's see here. So the area of a circle is pi r squared, right? So that's the area of the end of our circle. And then if we want to find the volume of the cylinder, that's simply pi r squared h, where h is the height of the shape, right? And we've got all the information there that we need. So to find our volume, it's going to be pi times radius squared, 3.2 squared, times the height, which is 7.8. Right? So I'm just going to go ahead and break out the old calculator. So pi 3.2 squared times 7.8. I'm going to punch it in all at once, just like a lazy person. I'm going to hit enter. There we go. That's all you got to do. Just when you're using your calculator, right? I know how this calculator works really well. So I know that was going to work out properly. But sometimes I've seen my students make mistakes where they'll end up like here with the pi and the 3.2 squared, but just the 3.2 has to be what's squared. So if you're ever in doubt, or if you want to check on your test, what you should do is punch them all in separately. So you can do your 3.2 squared, do that one separate, then times that one by your 7.8, then times that one by pi, right? And if you did it correct the first time, you'll see that it will work out the same. But when in doubt, or if you're on a test, or if you're unsure of anything, or unsure how your calculator works, always do it one step at a time, and you can just write it down on paper in between, right? A big part about math is reducing the potential for you to make easy mistakes, right? Because it's one thing to know the material, it's another thing to actually get all the arithmetic right. But anyway, this is 250.9 meters cubed. Cubic meters, right? Because this is meters, then it's squared, and this is linear meters here. The surface area Surface area of a cylinder is another great lesson because that one is covered a whole bunch of times in the various different courses that I do. Right? So the surface area of a cylinder is going to be the area of one end of the cylinder. Excuse me. We know that the area of one end of the cylinder is going to be pi r squared. Right? So that's just the top or the bottom. Now there's two of them. Drop a 2 on there. Right? But then there's the lateral area. There's the sides of the cylinder. How in the world do we represent the sides of the cylinder? Well, let me show you. Let me show you a little bit over here, maybe on my face cam. But imagine this sheet of paper was precisely a cylinder. Now, of course, I'm overlapping a little bit on the end here just to hold it together. But here, I've taken a rectangle and I've wrapped it into a cylinder, right? Okay. If I unroll the cylinder, see what this side here is? This side here, this side, let me get that, there we go. This side here, if I was to roll it up, that is the distance around the circle on the end of the cylinder. And what do we call the distance around a circle? Well, the distance around a circle, we call that the circumference, don't we? So, we already know. So we know that, say, the rectangle, right, that is unrolled from the sides of the cylinder, the side across the top of it is the circumference. And the other side, unsurprisingly, if we look at it again, the other side, this side, well, that's the height, right? That's the height of the cylinder. So what we end up with is just a flat rectangle that's been unrolled. This is the circumference of the circle, and this is the height. So the lateral area, which we're going to add to that one, is going to be the height times the circumference. Well, what is the circumference? Well, from up above here, we know the circumference is 2 pi r, and we multiply that by h. So we have 2 pi r squared plus 2 pi r h. Sometimes you'll see that written a bit differently. Sometimes you'll see it written with the 2 pi r outside. Maybe you'll see it written as 2 pi r outside of r plus h. Right? That works too. That's just a simplification. But this is generally how it'll be written on, if you're in my courses, this is how it's going to be written on your formula sheet. And this way is useful because we can look at this and know that this is the ends of the cylinder, and this is the lateral, or the sides. Or, well, side, one side, because it's a cylinder, it's round, it's just got doesn't have multiple sides, per se. Although, I guess we can kind of think of it as multiple sides. Anyway, I'm digressing. I never do that. I never digress. I only ever stay on topic all the time. So now we're just going to go and fill in from the equation that we have. So 2 pi times 3.2 squared plus 2 pi 3.2 7.8. That's going to give us 3.2 squared times pi times 2. Oh, get you guys to be privy to it. There it is. And see, I did it bit by bit. I did the 3.2 squared first just to make sure. Times by pi and is 2. So that is 64.34. I'm going to round it 2 decimal places. And then I'm going to add 2 times pi times 3.2 times 7.8. Now I use more brackets there than I needed to, but you know, it's for artistic purposes. In English, do you call this algebra? Yes, this would be algebra or pre-calculus. Pre-calculus is basically, well, this is definitely algebra. Anything up to and including, well, derivatives are usually I guess that's proper calculus. Anything up to and including logarithms is usually considered pre-calculus. And algebra is just sort of the term for how you move pieces of equations around to balance them. 156.83. So now I'm just going to go ahead and add those together, plus 64.34, and that equals 221.17. And that was going to be meters squared. It's square meters, right? Because we know this one has meters times meters, which makes meters squared. This one's in meters, this one's in meters. So these units are meters squared the whole way down. Okay, so that's useful. That wasn't a ton on review sheet number 2, but I think it's still super useful stuff. So I'm going to cross that one out. There we go, another one down. Great, good stuff. How far in are we? Hour and 15. Hour and 15 in. How's the stream looking? Am I coming through? Oh yeah, there we are. Take another sip from my beer mug filled with tea. Just a little proof here that it is tea. It's not actually beer with a tea bag in it. That would be odd. Okay. So now I'm going to switch to Math 1101C assignment number 2. Math 1101C assignment number 2. Here we go. So I've got well, this is the key already, but I'm going to be working through these guys. And I'm going to work through, let's see, questions 3A and B, 4B, and number 5. So 3A and B. Let's go up there and zoom in. Solve each system by substitution. Leave answers as fractions where appropriate. Okay, so they want us to solve these by substitution. Now, this is systems of equations. So we went over this a fair bit yesterday. But yeah, I showed several different ways of solving these. So right now, we're going to be solving specifically using substitution method. So this now is, and this will be sent out to a student as well. I believe this one is going to Adam. 1101C assignment 2. Okay, so 3A. The equations that we have are 2y minus x equals 11, and then 5y minus 3x equals 29. So solving by substitution, what that means is we're going to solve one of these equations to get one of the variables by itself first, so we know what that's equal to. The answer key that I have here brought up, they solve it to get y by itself. Well, they solve for x here, so I am going to do one differently. I'm going to solve for y first. Right? So what I'm going to do is I'm going to take this equation. This equation here is 2y minus x pi and the Fibonacci sequence. These are two mathematical laws. Disrupting my lesson? No, not at all. Absolutely not. Please ask questions. Pi is a mathematical constant. Pi is the constant that is basically the ratio of the circumference of a circle to the radius of it, right, or to the diameter, because that is, circumference is pi times diameter, and that's yeah, it's a non-repeating infinite decimal. It's like they say, right? Chuck Norris's pin is the last 4 digits of pi. I think that's a good joke. That one takes a second. It takes a special kind of nerd to get that joke. And the Fibonacci sequence, yeah, the Fibonacci sequence is that's the what they call the golden ratio, right? But the Fibonacci sequence is just when you take two numbers, say 1 and 1, and then you add the two together to make 2. Then you add those previous ones and make 3. You add those and make 5. You add these and make 8. You add these and make 13. You add these and make 21. Right? And that's sort of the sequence that keeps on going like that. I don't have any examples off the top of my head for applications of the Fibonacci sequence, but that is indeed what it is. right? It is used in say geometry. Um, anyway, 2y minus x equals 11. We do have that. And yeah, please, I am happy to answer questions. Um, Nature in general doesn't have a lot of constants. Well, I mean, it depends on what we define as nature, right? Like, for example, um, say the laws of physics. Like I know, say Newtonian physics. Obviously, that one does break down. That one breaks down as you approach relativity, right? Because then you have the whole sort of relativity, and then quantum mechanics, which is just an entire different kettle of fish, right? But when we have say constants like say the speed of light, right? That one has proven to be a most definite constant, at least so far. Um, I guess quantum entanglement maybe can transfer information faster than the speed of light theoretically. That's a real noodle boiler. I'm getting I'm getting way off topic here, but yeah. Anywho, math math does tend to have some constants in a perfect circle. Of course, pi is a constant that shows the relationship of the circumference to the radius or to the diameter. Right? So yes, I said I was going to solve this one to get a y equals. So to get a y equals, I'm going to move the x to the other side. Right? 2y equals 11 plus x. Right? Then we have y is equal to 11 over 2 plus a half x. Right? So I can now take this guy and substitute it back into this other one. Now, like I said before yesterday, whenever you're solving by substitution, which this equation does tell us that we have to do, you have to substitute back into the other equation. So if I took this one and substituted it back in here, I'm going to get 0 equals 0. Right? But if I substitute it into here, then we'll actually get something, although it's going to be a little bit unwieldy, but we're going to work with it. So we're going to have 5 times 11 over 2 plus a half x minus 3x. It's going to be equal to 29. Right? So that's going to give us 55 over 2 plus 5 over 2x minus, I'm going to convert this one now to be 6 over 2 x is equal to, so 29, I'm going to make this to be something over 2 as well, just so we can see when we're coming up. This guy is going to be a 58 over 2. Right? Now I'm going to go ahead and move all this around. So 5 over 2 minus 6 over 2 is going to be negative a half x. And I'm going to subtract the 55 over 2 from over here. So I'm going to get then 3 over 2. Right? So now all of a sudden it's looking a little bit simpler. So if a half x is 3 over 2, x is going to be equal to 3 over 2 multiplied by negative 2 over 1, or just by negative 2. These guys are going to cancel. We're going to get x equals negative 3. Okay? That was solving this one by substitution. Now that we have x equals negative 3, we can put that guy into either one up here, and we'll find out what y is. 2y minus negative 3 equals 11. So that's, of course, 2y plus 3 equals 11. 2y equals 8. Y equals 4. There we go. So now we know for these two lines, our point of intersection is going to be negative 3, 4. Okay, so that is, there we go. That is 1101C 3A. Let's do 3B as well here. There's a few more I'm going to do from this assignment. Then 3B, let me move this guy over. There we go. 3B gives us 6x plus 2y equals negative 3. And we have 4x minus y equals 5. So now, again, we're solving by substitution. I'm just going to pick whichever one of these looks easiest to solve for an individual variable. So I'm going to pick this one, and I'm going to solve for y. So I'm just going to glance at it and pick the one that seems like it's going to be the least work for me. So we're going to have 4x minus 5 equals y. Right? The y moved to the right, the 5 moved to the left. So now we have this one much quicker than we did previously. Well, I'm going to go ahead and fill that in to the other formula. Right? So 6x plus 2 outside of 4x minus 5 is equal to negative 3. 6x plus 8x minus 10 is equal to negative 3. 14x is equal to, going to add 10 over here, and that's going to be 7. So x is going to equal a half. Okay. So now I can just go back and stick this guy into one of the equations. 4, let's see, x is going to be a half minus 5 is equal to y. So 2 minus 5 is equal to y, negative 3 is equal to y. So your point of intersection here is going to be a half, comma, negative 3. Right? Okay, so that's one of the questions down I wanted to cover. Let's also then zoom this guy back out. Oh, that's in. In and out are different. Near, far. It's like I'm Super Grover. Sesame Street references. Boy, I am defining the cutting edge of internet memery with my Sesame Street references. So 4b was one that seemed a little bit sticky. What does 4 tell us to do? Solve each system by elimination. Leave answers as fractions where appropriate. Yeah. Now this guy, these questions here are some of those ones like I was saying the other day where you can't really metagame these guys because sometimes teachers throw in something mean where they make the answer totally crazily out to lunch, right? And it just means that, even though you're expecting it to work out to be like x equals a half and y equals 4, sometimes it'll be like x equals 17 over 38, and that's actually the right answer occasionally. That's just to trip you up a little bit. Ever heard of the human calculator? I have seen pretty impressive feats of people being able to do math in their head. Absolutely. Sure, I know when I was. It's amazing. It's a totally different skill too, and but it's incredible to see people that are really good at it. And like when I was when I there was a class I taught in the UK, and where was that? It was in Surrey. I had a top set year 7 class, so grade 6, and we did mental math drills like pretty much every few days or so. We would take a part of the class and do mental math drills. Let me tell you, like I've done a degree in math and been teaching it and stuff, and some of those kids were swift. They were really fast at doing math in their heads. Yeah, made Sir feel old in my mid-20s, boy. But yeah, it is incredible to see the kind of the amount of math that people can crunch in their heads once they figure out easier ways of doing it, because that's all that it's about. Need to be a mix between mean and nice to avoid giving students an easy time. Well, sure. There is. I mean, there's a little of column A, little of column B. It's never mean per se as firm, I would say. You do need to be firm, and you need to have boundaries that that if students try to cross them, you're going to push back, because they just had to know that. But that's not being mean. That's being firm, and being strict are not mean, right? But anyway, so this one is math 1101C, assignment 2 again. Oh yeah, yeah. I don't mean that mean is a bad word to say. No, I'm just saying that from a teacher's perspective, the point of discipline or something like that, or just being firm with deadlines or being firm with like um, I don't know, things like using calculators or phones on tests or something like that. It's just it's a way to show that there are boundaries and that you know basically the I guess the integrity of the teaching is and the integrity of the classroom and everyone else's learning is always super important. And just sort of rambling now. Right, so assignment two, so this is 4B. Right, if I when I link the students these videos to go watch, they're like, why are they just rambling? He's just talking about nonsense for like 40% of the time. A good 65% of the time. 5x plus 4y equals negative 14. 3x plus 6y equals 7. Now we're solving these ones by elimination. What elimination means is we want to get either the y's or the x's to have the same number, same coefficient, I should say, right? So we could either find the LCM of 5 and 3, it's 15, or the LCM of lowest common multiple of 4 and 6, which is 12. So I'm going to go ahead and use 12. So what I'm going to be doing is I'm going to be multiplying this top one, right? We're going to multiply that one then by 3. It's actually going to be this side by 3 and this side by 3 to be very accurate. And this one here, I'm going to do this side by 2 and this side by 2. It's totally valid to multiply a whole side of an equation by something as long as you multiply the whole other side of the equation by it, right? Because equations are balance beams. It's something balancing, right? And it's still balanced if both sides are perfectly balanced, as all things should be. Let me see. Let me see if I have a right. I don't have a double-sided knife, but let's see. Let's see if I can get this guy. Oh, 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 oh! Come on. There we go. Oh no, no, not perfectly balanced. Thanos would not be proud. Come on. There we go. Perfectly balanced as all things should be. There we go. That's my handy dandy bottle opener saw knife that I bought in Greece. Anyway, so this side of the equation, or this equation then, is going to become 15x plus 12y equals negative 42. This one here then is going to become 6x plus 12y is equal to 14. Right? Now what I'm going to do is I'm going to subtract this whole second equation from the whole first equation. 15x minus 6x is going to be 9x. 12y minus 12y is 0y. That was the point of doing this. Then negative 42 minus 14 is going to be a negative 56. Right? So if 9x equals negative 56, x equals negative 56 over 9. Right? Let's see. 56 cannot be divided by 3. No. 56 over 9. Are we... Yeah, we're done then. 56, negative 56 over 9, I believe is as simple as that. Yes, it is. Simple as that fraction is getting. What a pain. What a pain. But like I said, this is a good example of a question where you can't metagame it, right? You can't say, oh, well, the teacher probably didn't mean for negative 56 over 9 to be the answer that I got, so maybe I should go back and check. It's always reasonable to go back and check. You should always be going back and checking. But, you know, we're not always going to get the clue here that that this is, you know, not the right answer. Turns out it is, as long as I'm doing it right, which I hope. So then I'm just going to go back and put this into the equation up here, right? So we have, say, I'll use 3 times negative 56 over 9 plus 6y is equal to 7. Right? So 3 over 9 is going to, so this is going to be negative 56 over 3 plus 6y is equal to 7. 6y is equal to, so 7 is the same as 21 over 3 plus 56 over 3. 6y is equal to 77 over 3. Y is equal to 77 over 18. That is bonkers. But hey, look, y is equal to 77 over 18. X is equal to negative 56 over 9. So the key agrees with me that the point of intersection for these lines is going to be negative 56 over 9 and 77 over 18. Close the brackets. All right. Let's see. I also wanted to do question 5. Question 5. Keep on going here. Solve the system using any appropriate method. Leave answers as fractions where appropriate. Okay, so for question 5 then, we can solve it several different ways if we want to. The first one that I am going to show is going to be the same one that I just did here. Right? So I'm going to do negative 1 over 3 x plus 2 over 5 y is equal to negative 1 over 2. Then I'm going to have 2 over 5 x minus y is equal to 1 over 3. So again, what we're going to try to do is get there to be the same number of y's on the top and the bottom of these equations somehow. All right, or on one equation and the other. X's or y's. Well, I've already sort of given a tell as to what I'm going to do. I think I'm going to do y's. The way I'm going to do it is I'm going to multiply the top and the bottom, or left and right, sorry, of this one, right, by 5 over 2. So that then is going to become negative 5 over 6x plus y is equal to negative 5 over 4. And then from the other one, I'm going to keep that one the same. We're going to have, actually, I'm not going to write it out again then. I'm just going to put it here like this. Now what we're going to do is we're going to add these two together. Right? This one's going to be a little bit of a pain because we're going to have 2 over 5x. So we have 2 over 5 minus 5 over 6x. I'm just going to write it out like that because I'll write out the way I'm going to solve that there now in a second. And then we're going to have one on this side. We're going to have 1 over 3 minus 5 over 4. Right? So it did tell us to leave it as fractions where appropriate. So I am going to leave these ones as fractions because we can go ahead and do it. It's not super hard to leave these as fractions. So we're going to have top and the bottom of this one is going to be multiplied by 6. So it's going to be 12 over 30 minus 25 over 30 x is going to be equal to, let's do these over 12 then. So that's going to be, it's going to be 4 over 12 minus 15 over 12. Right, so that's going to be a negative 13 over 30 x is equal to negative 13 over 12. So then x is going to be equal to negative 13 over 12 multiplied by negative 30 over 13. These are going to cancel. This is going to become, let's see, 30 over 12 would be 15 over 6, would be 5 over 2. So x is equal to 5 over 2. All right. We're getting there. We're getting there. So I'm going to go back and I'm going to substitute this in now to one of the equations that'll make this as easy as possible. So we've got 2 over 5 x minus y equals a third. So 2 over 5 times 5 over 2 minus y is equal to 1/3. So 1 minus y is equal to a third. Well, I kind of already know what it's going to be here now, but 1 minus a third is equal to y. So 2 over 3 is equal to y. So we know that our point of intersection in question 5 then is going to be 5 over 2, 2 over 3, like that. All right? And now there appears to be some disagreement here. There appears to be some disagreement. Did I mess this one up somehow? My answer seems a little bit more sensible than what they got in the key, or is the key messed up? That's the question here. That's the question. Now we've got an interesting, you know, 2 minutes of content for my rapturous Twitch audience. So we have, let's see here. Did I do all these ones correctly? So this is going to be a check to see if I did it correctly. 5 over 2 times negative 1 over 2 is indeed negative 5 over 4. 5 over 2 times negative 1 over 3 is indeed negative 5 over 6. 5 over 2 times 2 over 5 is indeed 1. Okay, that's fine. So then I went and added these ones together. When I added these together, the y's cancel. This is subtracted, yeah. And these ones here are subtracted. This is still right. 5 over 6 and 25 over 30 are indeed the same. 2 over 5 and 12 over 30 are indeed the same. They're both multiplied by 6. 12 minus 25 is indeed negative 13. That's right. And a third is the same as 4 over 12. That's right. And 5 over 4 is the same as 15 over 12. That's also right. 4 minus 15 is not 13. There's my problem. There's my problem. See? There we go. I found it. We got there. So, with this much arithmetic, anybody can make a mistake, for sure. 4 subtract 15 is not 13. It is 11. 11. So it's a negative 11 over 12, which means these actually don't cancel, which means we got to write proper mess. So we've got a negative 13 over 30, x is equal to negative 11 over 12, right? So we have x is equal to negative 11 over 12 multiplied by 30 over negative 30 over 13. These ones still can cancel. This can become, we can divide both these, so that becomes 10 and that becomes, right, this becomes 5 and this becomes 2. But then what we have is x down here. Can we all still see this? Am I going way off the page here? Okay, so then x is going to equal negative 55 over 26. Negative 55 over 26. See, now if I, oh, positive 55 over 26, yes, of course, positive, because those negatives cancel. Don't mind me, see, one mistake compounds another. But 55 over 26, like, you see how dangerous it is to try to think that if you got a sensible sounding answer like 5 over 2, that you must be right. Like I got 5 over 2 here and I thought, oh, that makes total sense, I'm going to carry on. And it's not until I went back and checked that I noticed that, hey, the answer for x is actually 55 over 26, which definitely seems more like I made a mistake, but I did not. Not this time. So it just goes to show, always, always, always check your working, especially on a test, especially on a test. So So I'm going to go back and do the same one again. So 2 over 5 multiplied by 55 over 26. Subtract y is equal to a third. All right, so this becomes a 1 and this becomes an 11. This becomes a 1 and this becomes a 13. So we have 11 over 13 minus y is equal to a third. So 11 over 13 minus a third is equal to y. And they told us to leave it as fractions whenever possible. So what this means now is we're going to need to get the lowest common multiple of 13 and 3. Lowest common multiple of 13 and 3 is 39. So we're going to have 33 over 39 subtract 13 over 39 equals y. So then we have 20 over 39 equals y. There we go. And that, as we see, is the right answer. So we got there in the end. I sort of made some more work for myself because now when I do up this for the student, I'm actually going to have to, I'll just send him the stuff with the scratched out parts. It's no big deal, right? That's honest. It's raw. It shows people the true reality of doing math. It's doing the same things over and over again. Right, but anyway, the accurate point of intersection is going to be 55 over 26, comma, 20 over 39. That's bonkers. But that is right. So there you go. There you go, Adam. Hopefully you find a way to see that video. And if you don't, you find a way to at least read those ones. You take a quick look at my emails, see if I got anyone talking to me about other things they want me to go over on stream. Let's see here. Okay, I'm going to take a little bit of a break from the academic. We're going to take a quick pivot back to the refresher courses. So let's just make this a blank. Maybe I'll have to get some sort of screen background to go up there. So over here now, Prism Math Blue, page 240. So this is Prism Math Blue 240. So this page is all about properties of numbers, as we see here. And one of the nice things about the Prism Math sheets, right, is that it explains on the top what you're going to have to do in the sheet below, right? Now this sheet is on the properties of numbers. It's not a super important sheet to remember absolutely everything about, right? Because I'm not super concerned if you remember commutative, associative, identity, and properties of zero as the names. Although there is a question on the test about this, but I'll tell you right now, in other courses, you're not going to see a whole lot of like, which of the properties of numbers is this? You won't have to name it. You will have to know how to use it, and you will have to know when it comes up in algebra what it means, right? But the commutative property of addition and multiplication, commutative just means the order doesn't matter. So here, right, the order in which numbers are added does not change the sum. A plus b is the same as b plus a. Or the order in which numbers are multiplied does not change the product. So multiplication and addition are commutative, which means their order doesn't matter. Subtraction and division are not commutative. It's very important. right? Which is something that comes up in a lot of the refresher courses. People won't understand why sometimes I say, they'll give me a thing that's with division. Like oftentimes I'll see something like, say, people uh, will do like that, and they'll read that as six. Oh, I don't use my variable x when I'm writing like that. 6 divided by 9, right? But it's not. It's not 6 divided by 9. It's not at all. You could say 6 divided into 9 if you want to read them in that order, or how we would normally call this is 9 divided by 6. Now, this comes up in some of um, the refresher courses, right, when it's arithmetic, but sometimes it can be a bit tricky to get to realize what the consequences of saying it in a different order are, right? Because if you think of this as 6 divided by 9, if you did it in your calculator, you would do 6, then the division sign, then 9, you would get the wrong answer, right? So you have to know that this is actually 9 divided by 6, because the order does matter, right? But that just is because division is not commutative. So to go back over to the book, right? Commutative means the order doesn't matter. Associative, the grouping of add-ins does not change the sum. So if you have a bunch of numbers that are added together, you can put brackets wherever the heck you want. It's not going to affect the answer. The same with multiplication. Grouping of factors does not change the product. If you have a group of numbers that are multiplied together, you can stick brackets wherever the heck you want to. It's not going to matter. Right? The identity properties of addition and multiplication. So identities, that is relatively useful to know. The identity when you're multiplying is 1, because multiplying by 1 doesn't do anything. Right? The identity when you're or dividing. The identity when you're dividing is also 1. The identity when you're adding or subtracting is 0, because if you add 0, nothing happens. Subtract 0, nothing happens. And that brings us down to this one. Properties of 0, right? Adding or subtracting 0 is an identity, but multiplying or dividing with 0, well, that's a tangly one. Multiplying by 0 is totally fine. A times 0 is 0. And you can divide 0 by other numbers. You can do 0 divided by something else. That's 0. But you can never do a number divided by 0. And that does come up in a lot of the later courses, right? Because 0 is dividing by 0 is what gives us non-permissible values, or NPVs, in a lot of our later courses. But we can divide 0 by other things, and that's totally fine. Okay, so with these ones down through here, name the property shown by each statement. You're just going to go through and name which of these 4 applies to these ones. So x times 1 equals x, well, that's an identity. It's an identity because we know that nothing happened here, and if a math operation happens and it causes like nothing to change, then that is identity. Right? For 2 here, this one's commutative because the order switched and it didn't affect it. This one's commutative because the order of the A's and the B's switched and nothing got affected. Right? But the student specifically asked for these next ones. So let me scroll this. We have here now the property of 0. So all you have to do, rewrite each expression using the property indicated. All you really need to do here is show somehow what the result would be if you used this sort of property. That's an awkwardly phrased question. But 8a times 0 gives you 0, right? So that's the property of 0. 1 times 3 plus 11 is just 3 plus 11. That's the identity. Nothing happened. 3w plus 0 is equal to 3w. So all you're really doing is just figuring out what these ones are. The only ones that are a little bit odd, a little bit strange, are the commutative and associative ones. Well, all the commutative one means is you just show that the order can change, and it's fine. The associative ones, you show that the brackets can change, and it's fine. But this sheet is not, again, this sheet is not terribly important. You're not going to be quizzed on these numbers very much, on these names very much, but you are going to need to know that say the order of addition and multiplication doesn't matter. God, I'm hiccuping. And you'll also need to know that, say, um, multiplying by 0 makes things 0, and dividing by 0 makes things explode. All right, so don't do that. Dividing by 0 causes black holes. That's science. It's just well known. It's well known to science that dividing by 0 causes sort of the universe to crumple in on itself and lose information. But information can never be lost. So what happens? What happens indeed? We have one more thing that I have on the slate to get to today. Math 1101C worksheet number 5. Now, Math 1101C worksheet number 5 is kind of like what I was doing yesterday in that course, which is to say a heck of a lot. So I will be needing to make a full answer key for this assignment. So y'all can hang out and watch me do that. And I'll just yammer while I'm doing it. It's difficult to zoom out enough so we can see that full thing up here. Let me switch over to my fancy old document display. Here we go. So set up a system of equations for each of the following problems, and then solve using methods learned in this chapter. Complete this in your notebook. Two numbers have a sum of 10. The final number plus 3 times the second number is 24. Determine the numbers. Now, the math that's going on here is not super difficult. It's just sort of phrased strangely. All right, so this is actually, because I'm going to make this and use it as an answer key to submit. See my wonderful little duct tape indication of where I need to put my paper. You see, duct tape. It's the handyman's secret weapon, I tell you. That's one of the ways you can know that I'm Canadian, is that I have duct tape in my house. It's a legal requirement if you're a Canadian male to have at least one roll of duct tape. That's actually true. Math 1101C worksheet number 5 key. Here we go. Here we go. Two numbers have a sum of 10. All right, sorted. The first number plus 3 times the second number is 24. Determine the numbers. There we go. I mean, now we've got something that's pretty sensible for, whoa, hold on. Hold the phone. There we go. There we go. Thanks, document cam, or document feed. So, x plus y equals 10, x plus 3y equals 24. Easy, it's just a system of equations. We can go ahead and subtract and get rid of those. So we're going to have then y minus 3y is negative 2y. 10 minus 24 is negative 14. Negative 2y equals negative 14, so y equals 7. And if x plus y is 10, x plus 7 equals 10, x equals 3. Right? So, I mean, yeah, if you're doing something like this, right, it might, I've got to get a better solution for that switching to the document feed there than that. That's inelegant. If you see a question like this, it looks more daunting because it's written out in words, but as you see there, that was quite a lot simpler than like all the other questions that I've solved in this same course so far. Question 2. A coin box of a vending machine contains 620 in dimes and quarters. 32 coins in total. Determine how many of each coin is in the box. Now this one, this has a little bit of interesting stuff to it, right? Because here, the coin box of the vending machine contains 620 in dimes and quarters. Well, of course, I'm going to change it to cents instead of using dollars. So dimes, there's some number of dimes, right? Dimes are each worth 10 cents, so 10x. Some number of quarters, 25 times y, that gives us 620. So I've removed the decimals here now because I'm working with cents and not dollars. Right? So there we go. We just stick that one back up in the corner. So our other equation then is going to be there are 32 coins in total. So x plus y gives us 32. So now what do? What indeed? What I'm going to do is I'm going to go ahead and I'm going to use a different method to solve this one now. I'm going to go ahead and use substitution method. So I'm going to say that y equals 32 minus x. That's not hard. I just took this x and moved it over, right? So now what I'm going to do is I'm going to substitute that one back into this one. It has to be the other one. So I'm going to have 10x plus 25 times 32 minus x is equal to 620. 10x plus 25 times 32. Well, 32 divided by 4 is 8. So that should be 800. Right? Let's see if my mental math was correct. It was. Look at that. Right? That's a callback. That's what I was saying earlier. The the basics of mental math is figuring out shortcuts. Mental math is a great exercise for lazy people because it's, I mean, not a physical exercise, because it's all about, finding ways to make your work easier. So now I'm going to have a negative 15x equals a negative 180. So x is equal to 180 over 15 should be 12. Yeah, there we go. Good stuff. All right, so x equals 12. So now we have our 12 plus y equals 32, which means y equals 20. Easy. So now in number 2, then, we know that if we switch back over, we will see that coin box of vending machine contains 620, 32 coins. Determine how many of each coin is in the box. That's going to be 12 dimes and 25 quarters. Sorry, 20 quarters. 12 dimes, 12 a dime, 20 quarter. Easy. All right, question 3. When one number is added to double another number, the result is 29. When double the first number is added to the second number, the result is 16. Determinerino the numberinos. Okay, so one number, x, is added to double another number. The result is 29. I don't know, I'm talking through this rather painstakingly, but that's what the whole point is, right? Is to convert the language into a math expression. So then the next one, what is, when double the first number is added to the second number, the result is 16. So when double the first number is added to the second number, the result is 16. Determine the numbers. Okay, so now I'm going to go ahead and I'll do the elimination method again. So I'm going to multiply this by 2 and this by 2. So we're going to have 4x plus 2y equals 32. We have our x plus 2y is equal to 29. So now if I go ahead and subtract this one from the other, I'm going to get 3x is equal to 3. So x is equal to 1. Well, look at that. Pretty good. Then, now that I know x is equal to 1, I can go back and substitute that into either of my equations. 1 plus 2y equals 29. 2y equals 28. y is equal to 14. Good. Good stuff. I think that's fairly readable up there in the corner. Yeah, I think that's pretty good. So let's keep on going then. Let's keep on going with this answer key. I'm going to do this until roughly 2:30 Newfoundland time, which is another 25 minutes for me. So I hope y'all are comfortable there. Anyone watching the stream, I mean, you can feel free to speak up and suggest me any questions to do. So number 4, a hockey team bought 70 pucks for a total cost of $120. The pucks used for practice cost $1.50 each, and the pucks used for games cost $2.25 each. How many type of each puck did the hockey team buy? $70 pucks cost a total of $1.20. The pucks used for practice cost $1.50 each. Pucks used for games cost $2.25 each. It's oddly phrased for sure, but we'll get there. The way that we figure this one out, well, we know that there's 70 pucks. Some are for practice and some are for games. So I'll call those P and G. But we know that there was 70 bought in total. So P plus G is going to equal 70. Right? Let me switch back over to the other sort of feed here so we can see it a little bit better. Then what we have for the next one is pucks used for practice cost $1.50 each, and the pucks used for games cost $2.25. So the practice, so $1.50 times the practice ones plus $2.25 times the game ones are going to equal the total amount of money that they spent, which is $120. So the tricky part here is getting these two equations, right? Once we have these, it'll be relatively easy to go ahead and to get the rest of it. What I'm going to do now is I'm going to do these ones via elimination method. So I'm going to multiply this one here by a 3 on the left and a 3 on the right. This one here by a 2 on the left and a 2 on the right. Right? The reason I'm doing this now is so that these will cancel. Right? So what we're going to be left with from the top is 3p plus 3g is equal to 210. We have on the bottom is 3p plus 4.5g is going to equal 240. So I'm going to go ahead and subtract these now, as it's my systems of equations that I'm working with. 3p minus 3p is 0p. 3g minus 4.5g is negative 1.5g. 210 minus 240 is negative 30. So g, not y, g is going to equal 30 divided by 1.5, which is going to be 20. So we know that they bought 20 game pucks. If they bought 20 game pucks, well, we know that P plus 20 then is going to be 70. So it means we know that P is going to be 50. So there we go. It takes a little while to get to it, right? Because there is a fair bit to do. But we do get there in the end. Let's carry on, because I have to do this at some point. I would like another 20 minutes of content or so. So let's pull it up. Let's pull it up. Nicole purchased 5 boxes of chocolates and 3 bags of candy for $12.05. Cost of a box of chocolates and a bag of candy were reversed. Then it would cost $11.07 for the same order. Okay, that's a very odd way of phrasing that, but we'll translate that into math, no problem. Right? So 5 times chocolates. Oh, I'll call that B because it's boxes. Boxes of chocolates and bags of candy. B of C and B of C. Come on, people. That is rough. That is rough. I'll just call them B and C then. Fine. Boxes of chocolate and bags of candy. 5 boxes of chocolates plus 3 bags of candy is going to equal 1205. But if they were reversed, so if we had 3B plus 5C, that would give us 1107. Right? So again, I can solve these via systems of equations, or I can solve these via substitution. Well, there's all system of equations, sorry. I can either solve it with substitution or with elimination method. I'm going to go ahead and do elimination method like I've been doing. Yeah, I'll multiply this one by 3 and this one by 5. We just need to make it so that one of the coefficients, one of the variables has the same coefficient in the first one and the second one. So that is going to be then 15b plus 9c is going to equal 36.15. Down here we're going to have 15b plus 25c is equal to 55.35. Okay, so I am now going to go ahead and subtract. So we are now going to have 9 minus 25 is going to be negative 6c. That's going to be, boy, 1920, negative 1920. 36.15 minus 55.35. Negative 1920. Yeah. Maybe it doesn't count as figuring it out in my head if I try the calculator afterwards just to make sure. Anyway, I am not going to do this division in my head though. 19.2 divided by 6 gives us 3.20. So that's what the candy costs, $3.20. So now to go back up, 5b plus 3 times 320 equals 12.05. 5b plus 9.6 equals 12.05. 5b equals 2.35. 2.45, what am I saying? 2.45. 2.45 divided by 5 is going to be b equals 0.49. Which, hey, you know, someone who made this question actually took the effort to make the numbers work out to something half realistic. Look at that. So yeah, Nicole purchased 5 boxes of chocolates and 3 bags of candy. Well, then the boxes of chocolates cost 49 cents. The bags of candy cost $3.20. Yeah, let's see. Let's keep on going then. Let's get this answer key made. Okay. That was, yep, I was up to question 6, wasn't I? Question 6. Question 6 says, there are 27 students in Ms. King's math class. The number of girls in the class is 3 more than twice the number of boys. Determine how many boys and girls are in the class. Okay, so all the students are either going to be boy or girl. So it's boy plus girl is equal to 27, right? And the number of girls in the class is 3 more than twice the number of boys. So let's write that out. The number of girls, we're using G, is, that'll be an equal sign. That's going to be 3 more than twice the number of boys. Yep, so that's right. So G is equal to 3 plus 2B. So we could do elimination method here, but that's going to be a little bit more work. It's already written in substitution method for us. It's done, right? That's fairly straightforward. So I'm just going to go back and substitute. I'm going to say B plus 3 plus 2B equals 27. So then 3B is going to equal 24. So then B is going to equal 8. Hey, look at that. Nothing to it. And then 8 plus G is equal to 27. G is going to equal 19. There we go. Question 6 down. Question 7. Sum of a number and twice a second number is 16. So the sum of a number and twice another number is 16. Then the first number is 4 greater than the second number. So the first number is 4 plus the second number. Right? So now what do? Well, I'm going to go substitute. 4 plus y plus 2y equals 16. 3y equals 12, y equals 4. X equals 4 plus 4, x equals 8. There we are. Oh, tearing through them now. The larger of two numbers is equal to 3 times the smaller number. If twice the larger number is added to 3 times the smaller number, the sum is 27. Determine the numbers. It's a lot of words. So for 8, the larger of two numbers is equal to 3 times the smaller number. So x is equal to 3 times y. If twice the larger number is added to 3 times the smaller number, wait, are they seriously giving us that? Twice the larger number is added to 3 times the smaller number. The sum is 27. Okay, sure. I mean, it's odd that they chose this one a little bit. Sorry, SC time. I don't I don't really speak anything other than English. I'm sorry. I didn't even learn Spanish in school, so I went to school in Canada. So parlez-vous avec moi, s'il vous plaît? I don't know. What I have here now, I've got x equals 3y. 2x plus 3y is 27. So I can go ahead and substitute. I can put 3y in place of the x in here. So we can call this 2 times 3y plus 3y is equal to 27. So then we end up with 6y plus 3y is 9y is equal to 27, or y is equal to 3. And since x is equal to 3 times 3, we know that x is equal to 9. It's straightforward stuff, right? I am just sort of tearing through a few of these here now, because I do need to make this key, and a student did submit this one. Right? But if anyone has any suggestions for questions to solve, I will gladly go over that. Three times Nancy's age is 6 more than twice Roger's age. The sum of their ages is 32. Determine the age of each person. Okay, so 3 times Nancy's age. So 3 times Nancy's age is 6 more than twice Roger's age. So there we go. The sum of their ages is 32. So Nancy plus Roger equals 32. Determine the numbers. So we can easily go ahead now and solve for one or the other, right? Um, let's see, what is the easiest way of doing this one? I'm going to rearrange it to be, say, n is equal to 32 minus r. Rearrange that guy. So I'm going to go ahead and substitute that back into the one above. So 3 outside of 32 minus r is equal to 6 plus 2r. So 3 times 32 is, of course, 96. 96 minus 3r is equal to 6 plus 2r. So 90 is going to equal 5r, right? 18 is equal to r. Pretty straightforward. And then we know that n is equal to 32 minus 18, right? So n is equal to 14. Easy. Right, the sheet might be a little overlong for the types of questions it is, but if you're bearing with me while I'm going through these, um, thanks for sticking it out. Let me try something new here. Let me try and see how's that light level looking. That's maybe a little better, but it does make my face cam a bit obvious. Obviously now it's brighter over here than it is over here, so it's maybe not the finest solution for my face cam that there's ever been. So twice the length of a rectangle is equal to 5 times its width, right? So twice the length is equal to 5 times its width. Just write those down. Oh, I'm getting those lines across my stream again, aren't I? Yeah, I'm gonna have to shut that fluorescent light off. It comes off weirdly. Okay, so number 10, perimeter of the rectangle is 77 meters. All right, so that's important to know. So perimeter is 2 lengths plus 2 widths, and that is equal to 77. So they've even already told us that 2 L's are equal to 5 W's. So this is a little bit of a cheat, but I can go ahead and just stick 5 W's in there as place of these 2 L's, right? We can call that just 5W plus 2W is equal to 77. 7W is equal to 77. W is equal to 11. Easy, right? And if W is equal to 11, we have 2L is then going to be equal to 5W, which is 55. So L is equal to 55 over 2, which is going to be 27.5. Right, so now we've got numbers 11 and 12 left. Almost done. Almost done this sheet. Feels good. For number 11, Rachel sold 7 adult tickets and 3 student tickets for a school play and collected $10.25. Her sister sold 3 adult tickets and 7 student tickets and collected $7.25. Determine the cost of each type of ticket. So 7 adult plus 3 student was equal to $10.25. 3 adult plus 7 student. Why do they keep doing the same numbers on this sheet? 725. Okay. So here we'll need to multiply both of these to get to the lowest common multiple, right, of 3 and 7, because I'm going to do elimination method. So what I'm going to do is I'm going to multiply the left-hand ones by 3. I'm going to multiply the right-hand ones by, or sorry, Left and the right sides will be multiplied by the same number. The top one's by 3, the bottom one's by 7. So it's 21a plus 9s is equal to 30.75. 21a plus 49s is equal to 7 times 25 would be $1.75. 7 times 7 is 49. So it's 50.75. Right? Let's just combine 25 times 7. Yes, 50.75. All right. I am going to go ahead and subtract. 21 minus 21 is 0. That was the whole point. 9 minus 49 is going to be negative 40s. And 30.75 minus 50.75 is going to be a negative 20. So s is going to equal 0.5. Or 20 over 40, 2 over 4, 1 over 2, 0.5. So the student tickets are 50 cents, turns out. So let's go back up to one of the originals. 7 adult plus 3 times 50 cents is equal to 10.25. 7a is going to be 10.25 minus $1.50. So 7a is going to be, so it's 875. I'm not going to do 875 divided by 7 in my head. That was $1.25. Maybe I should have. Maybe I should have done it in my head. Either way, there we go. So that is the result for that one. I have got one more question to do. I'm going to cram that guy in at the bottom here, because I've got enough room on my paper probably. Lisa, your teeth are big and green. Lisa, she smells like gasoline. Lisa, she purchased 5 pencils and 3 pens for a total of $8.52. So what am I going to do here? I'm just going to call these x and y. So 5x plus 3y is equal to 8.52. Chad, it's very Chadly. A very Chadly thing to do is to purchase 2 pencils and 4 pens. So 2 pencils plus 4 pens equals 5.76. Now, unfortunately, none of these ones have had much of a teachable moment sort of twist in them. But we're going to get through it because this is the last question, the last one. So I am going to go ahead and multiply these ones both by 2. I'm going to go ahead and multiply these ones both by 5. So we're going to have 10x plus 6y is equal to, so it's going to be 16 plus $1.04, so it's 17.04. We're going to have 10x plus 20y is equal to, 76 times 5. Well, 75 times 5 is $1.50, so it's be $1.55. No, that's 25 times 5. What am I even saying? 75, no, 75 times 5. 2 75s are $3. So the 4 set. I've been doing arithmetic for 2.5 hours. Just bear with me, people. I'm gonna tap out. I'm gonna do that one by a calculator. $28.80. No shame in using a calculator, even when you're the teacher. Hopefully. So we're gonna go ahead and we're gonna subtract. So it's negative 14y is equal to, you know what? 17.04 minus 28.8 kilobaud modem equals negative 11.76 divided by negative 14. It's going to give us y is going to be 0.84 or 84 cents. So then I'm just going to continue question 12 over here. Maybe it's not the most elegant of answer keys that I've ever written. We're going to have then 5x plus 3 times 84 equals 8.52. 5x equals 8.52. Subtract, okay, so 8 times 3 is 24. It's 12. 24 and 12 would be 25.2. Right? Yep, that's right. So then 5x is going to be, hey, that's fairly easy. 5x is going to be $6 dues. So then x is going to be 6 divided by 5, which is $1.20. There we go. There we go. All right. Math 1101C, well, 1101C worksheet 5 key done. Sorted. All right, and that was everything I said I was going to get through today, and we are exactly 2:30. Look at that. Look at that. All this extra work that I have made for myself is about to end for the day. Great. Thanks for sticking around with me, guys. Whoever's there live watching, you're very welcome to, in the future at any point, submit questions to me. I am working on getting some other social media stuff ready so that people who find me randomly on Twitch can also submit stuff to me to solve for the next day. For now, you can drop it in chat. Yeah, if you've got something, or if you have my email, my school email, you can send me any questions that you might have to go over. Yeah, I'll have some Twitter details in the next few days, and people can drop some questions on there as well. For any students who might be watching this after the fact, yeah, you can, if you've if any of these questions were for you specifically, I will have linked them to you as well. But there is plenty of content in here that might be good just in general. So if you need, say, a sleep aid, say you've run out of NyQuil, yeah, just watch the past broadcasts and you'll go straight off into dreamland. No problems whatsoever. I don't even have like K-Rock in the background, right? Candace Udel's not even, yelling ads at me all day long. So it's really sleep inducing here. Anyway, yeah, this was a good day too. Thanks for joining me, folks, and yeah, have a nice rest of your day. And yeah, hopefully, I'll leave you with a bit of word of wisdom from Red Green, right, in these trying times. That this might be an unprecedented situation, of course, but we are all in this together. And keep your stick on the ice. Right? It's a good sign off. Yeah. Just borrow someone else's line. It's no big deal. It's plagiarism. Who cares, right? I'm only an English teacher. Who cares about plagiarism? It's not a big deal. See ya.